Hi guys, welcome to the first video of the series on geometry. Today I am going to present an interesting question about the geometric center, also known as the centroid of a triangle, and its connection with vector algebra. Let's get started. Let R1, R2, and R3 be the vectors joining the origin of the Cartesian coordinates to the vertices of the triangle ABC. Let P1, P2, and P3 be non-negative real numbers such that P1 plus P2 plus P3 is equal to 1. Show that the point P1R1 plus P2R2 plus P3R3 lies in the interior or on the boundary of ABC. Pause the video and see if you can come up with a solution. Alright, let's get started. Let R be the vector which joins the origin to the desired boundary or interior point. The idea is that I can draw infinite number of lines which pass through the head of vector R and cross the triangle. For instance, this green line or this line. But if I draw parallel lines to any side of the triangle, for instance side BC, you will see that I can use the basic rules of plane geometry to find proportions between the line segments. Let's draw them. And represent the intersection points by D, E, and F. We can decompose vector OF as the sum of three vectors. R equals OF is equal to OA plus AE plus EF. And from the figure, you can see that AE is parallel to vector AC. AE is parallel to AC. AE is equal to alpha AC for some alpha between 0 and 1. In the same way, EF and ED are parallel to each other. EF is parallel to ED, and therefore we can write EF equals beta ED for some beta between 0 and 1. Because the green lines are parallel, the triangles ADE and ABC are similar because they have three equal angles. So ADE is similar to ABC, and therefore the ratio between AD and AB or AE and AC is equal to the ratio between ED and CB. We can write AD to AB is the same as AE and AC is the same as ED and CB. Let's call these relations 1 and 2. And here from 1 we can see that ED is equal to alpha times CB. And from 2, we can see that EF is equal to beta times alpha times CB, and we name it 3. I represent the original relation by star. From star and 1 and 3, we can write R is equal to OF is equal to OA plus AE, which is alpha times AC, plus EF, which is beta times alpha times CB. And we also note that OA equals R1, AC equals OC minus OA, which is R3 minus R1, and CB equals OB minus OC, which is R2 minus R3. R equals OF equals R1 plus alpha times R3 minus R1 plus beta times alpha times R2 minus R3. So we can factor the vectors here and simplify R even more by factorizing the vector elements on the right hand side. So R equals R1 times 1 minus alpha plus R2 times beta alpha plus R3 times alpha minus beta alpha. Let's define P1 equals 1 minus alpha, P2 beta alpha, and P3 alpha minus beta alpha. Therefore, R is equal to P1 R1 plus P2 R2 plus P3 R3. And we can see that P1 plus P2 plus P3 is equal to 1 minus alpha plus beta alpha plus alpha minus beta alpha. So plus beta alpha here minus beta alpha here cancel out. Alpha here minus alpha cancel out. And the result is 1. And the proof is complete. A special case is when all these coefficients are equal. P1 equals P2 equals P3 equals 1/3 because their sum is 1. In this case, the interior point is known as the geometric center or the centroid of the triangle, and its coordinate is given by RG equals 1/3 of R1 plus 1/3 of R2 plus 1/3 of R3. The centroid.